Code 39 says, suppose the boat is traveling on a river at velocity v vector and speed of 20 miles per hour. So we have a river. Say which direction it's going? Not yet. Okay, so I'm just, v vector is 20 miles per hour. Further, suppose the river has a current of C and a speed of 5 miles per hour. Okay, we can write that in there. The river is going 5 miles per hour. Under what conditions will the speed of the boat be 25 per hour relative to the land alongside the river? Create a geometric argument for a situation where the relative speed of the boat is not 25 miles per hour. Okay, so I think this is pretty straightforward, the first part at least. If the boat, right, is traveling at 20 miles per hour, and the river is going 5 miles per hour in the same direction. I mean, the mathematical way where we want to look at this is that the two vectors are adding up, and their direction is the same. So the speed of the boat relative to the bank is 25 miles per hour. We'll just add the vectors that way. Is there any question about that? That seems just trivial. Right. Under what conditions will the speed of the boat be? Oh, that's the conditions, they'll be 25. Create a geometric argument for a situation where the relative speed of the boat is not 25 miles per hour. I'm not quite sure how rigorous an argument they're looking for, but it would seem that if the boat were traveling in any direction, but exactly opposite, or I'm sorry, exactly coincident with the direction of the river, well, in the worst case, it's going in the opposite direction, right? You'd be subtracting the velocities by adding the vectors. So it would be going 15 miles per hour. In the other situation, you'd have a triangle where you'd add up the velocities, and what you have here is a triangle with 3 sides. One of them is 20, one of them is 5. The third side is always less than the sum of the other 2 sides. So I think that's the geometric argument they're looking for. Any questions about that, or this is more of a, it's less can you calculate accurately with vectors, or can you get a feel for what they're doing kind of question. All right, move on. So 41 says, vectors express quantities that have magnitude and direction. Is it possible to describe the zero vector? Write an explanation of the zero vector and explain how it is expressed symbolically. Okay, so here they're putting u on this. Yes?
It's actually 44.
Didn't someone ask for 41?
No.
No. Oh, I'm sorry. Okay, I misheard. Let me move on. Does everybody understand the zero vector? It's just a vector which has 0 magnitude, and therefore its direction is kind of meaningless, or the way we would describe it in math, we would say it's in every direction. Right? So, for example, the zero vector would be parallel to any other vector, but it would also be perpendicular to any other vector. So, okay, well, that was 41, so let's move on. 44, a hanging frame. As seen, let me put the photo up here. Oh. Here's our hanging frame. So I'm going to wall with the center of the hanging cable on the hook. The angle of the hook is 100 degrees. And the frame weighs 8 pounds. And the frame weighs 8 pounds. Determine the tension in each side of the hanging cable and express the tension as a vector in components form. Okay, so first we have to kind of figure out what's going on here. We have a weight, which is 8 pounds. That's a vector force going straight down along the direction of gravity. It's being held by 2 wires, and I believe they mean by the angle at the hook, this angle here, which is 100 degrees. So you can see that there's a tension along this wire and along this wire, and it's nice. This is symmetric, so we only have to worry about one of them, right? And each of these vectors will have components, right? There's a component pulling sideways, and there's a component pulling up, which is the 2 of these components pulling up are what's offsetting the 8 pounds of gravity. Since this is symmetric, we can know that this angle here is half of 100, or 50. And now what do they want us to find out? Determine the tension in each side of the hanging cable and express the tension. Okay, let's do that first. So we know this vector here and this vector here are equal, so they each have to do what? To offset the 8 pounds pulling down.
4?
Each have to be 4. So I'm going to draw kind of a separate diagram here to make this clear. So we have a force of 4 this way. We have an angle here of 50 degrees, and we don't that much care what this vector is, because we know there's an opposite and equal vector going in the other direction offsetting it. So it's hard to write clearly sometimes with these markers. So we really, this is left to be, this is a trig triangle problem we found. We want to know what this vector is, or I'm sorry, in the wrong direction because it's pulling back. So how would we find the value of, we'll call this x, knowing this angle is 50 degrees and this is 4? What trig function are we going to use? Okay, the sine of 50. The sine of 50 is going to be what? Careful, x is the hypotenuse. So we have sine here. Sine of 50 degrees equals 4 over x, or x equals 4 over the sine of 50 degrees. Okay. We can use the calculator to figure out that value, but that's going to tell us the tension on each cable. Okay, what's the last part of this? Determine the tension each side hanging. Express the tension as a vector in component form. Okay, so they're not going to let me get away with skipping this other vector, right? So the vector starts, this is its tail and this is its head. And so we know one of the components, right? We know we already know this component, right? That's the y component, so that's 4. We know the total, this x, which is the hypotenuse. So how would we find the other leg of this triangle? I hope you guys are just being quiet today. I have a right triangle and I know 3 sides. Yeah, Pythagorean theorem. So I'm going to square this 4 over sine of 50 degrees and subtract 4 squared and find the square root, and that's going to be my value. Okay. All right. Any other questions about this? So that was 45. Oh my, this is complicated. Aircraft heading. Now, bear in mind, of course, that for aircraft, up north is 0 degrees and we go clockwise. Suppose an airplane is flying from Minnesota to Los Angeles at 605 miles an hour at a fixed altitude with no wind factor. Okay, so I'm going to just kind of draw a little map here. There's Minnesota, and here's LA. And we're traveling at 605. That's our velocity. The velocity may be considered a vector. Explain why it is a vector. Okay, and describe the two important parts of the vector. I hope at this point you all would be able to say a vector quantity is one with direction and a magnitude. In this case, the magnitude is the speed of the plane. Describe the two important parts of the vector. I suppose you could kind of misinterpret what I think they're asking for you. Well, it's the x component and the y component, but I think what they really mean is it has a direction and a magnitude. Express the velocity of the plane, this is part B, a vector as a vector in component form. Okay, well, we're assuming, of course, the Earth is flat, or at least close to flat for this distance here. So we have a component, a y component, which we can see is going to be negative. We have an x component, which is also negative, flying east to west. And we know that the hypotenuse of this, the total velocity is 605. Oh, I'm sorry, I didn't notice here. East, traveling to Los Angeles, east 249 degrees north. Okay, so looking back at our little rosette here, what is 249 degrees? This is from north to east is 90, 180. This would be 270, so we're down here in the third quadrant. What's 249 minus 180? So this would be 69 degrees. So this angle here is 69 degrees. So now we have, again, a simple trig triangle problem. What are we going to use for the y component here? We have hypotenuse is 605. We have this angle, and we have what's want to find y? What do we?
Cosine?
Cosine, yeah. So the cosine of 69 is y over 605. That tells us the y. And similarly for the x component, we're going to use
Sine.
sine. Yeah. Is that enough?
No.
No? You want me to find the answer, or do you want me to go on to part C?
That's
Okay, thank you. C says, find the magnitude of A. Well, we know it's 605 miles per hour, right? And describe its significance in the context of the problem situation. That seems like a real easy question. It's just significance. The magnitude of significance is the speed of the airplane. Since there's no wind, it's the ground speed. Okay. All right, and then it was 49. Someone say 49? Oh, there it is. Stretch your mind. Okay. Your task is to make an argument for each of the following facts. Your argument may be graphical and or symbolic. Right, so 49 says C plus K, which are scalars, times the vector AB, which is the vector going from point A to point B, is equal to C times AB plus K times AB. So we gave this a name. Anyone recall the name of this property? Give it a name on Monday. Important property. Distributive property. Right? It's a little like the strict distribution on just scalars or numbers, but here we're distributing two scalars over a vector. And the question here is this valid? Now, a graphical representation, you might draw a vector, right? You might indicate that you're multiplying the vector. Let's, for the sake of argument, say it's a unit vector. And the resultant vector is C plus K. Well, you might say, look, wait a minute, if we multiply this unit vector by C, and then we multiply it by K and add it, we would get presumably the same vector. That would be a graphical way to show it. And then algebraically, you could give AB some component values. You could say this is C plus K times, let's say, position vector XY. And you could show that using multiplication of a vector by a scalar, that you can break it up into this. I'm not going to show you how right now unless you ask me to do that. It's kind of a little basic vector proof. You want to see that, or is it obvious?
Let's see it.
You want to see it? Okay. It's kind of mundane, but that's fine. I like mundane. All right. So we say our vector has components x and y, and we're multiplying it by the scalar c plus k. So we use the usual method of multiplying. We say that's going to be c plus k times x, c plus k times y. Well, now we're just going to fall back on the distribution law numbers that we know so well. We should. C plus k times x is cx plus kx. C plus k times y is cy plus ky. Okay. Now we're going to do addition in reverse on this vector, right? We know that cx, cy plus kx, ky is just going to be equal to cx plus kx, and so that's the way we do addition. We're just kind of reversing it. And now we're going to, now I have to look and see if I'm going in the right direction. So now I have to undo the multiplication here, and I'm going to rewrite this vector as c x comma y plus k x comma y. But that's, of course, just my c ab plus k ab. A lot of mathematical proofs are like this, where you just merely kind of write down what's going on, and you rearrange things, use properties you know, like distribution of addition. And that's actually good we went over this, because our next section, which is going to be on trig identities, we're going to do a lot of stuff like this, where you transform one form of something to another, proving their equality. Okay, are there any other homework questions? Okay. All right. Before I just jump in, let me talk a little bit about what we're going to do today. We're going to look at something called the dot product. It's we'll call it for the moment, a feature of vectors. It's a very important feature. Any of you who do any physics or probably engineering will come across this. We're using a kind of a geometric vector now, and it's very common. But if you go on in mathematics or other subjects, you're going to find that vectors are generalized into a very abstract object. And they will have applications in all sorts of odd areas. You will find it, certainly if you go into, say, business models, you're going to be doing a lot of very abstract modeling, and you'll end up with using vectors that can be very multidimensional, describing, say, different properties of an economy or of some economic object. And the dot product can play a very important role. Unfortunately, we're not going to get in as deep as I would like, but you should keep that in mind. This is very foundational stuff. Okay, so last Wednesday we started looking at vectors, and we found that vectors can be added, subtracted, multiplied by a number. So the question arises, are there ways to combine two vectors, not in an addition kind of way, but in a multiplication kind of way? Use the word kind of explicitly. I'm not talking about the direct multiplication, but something else. As it turns out, there are two different ways to do this, at least two different ways. One of them is known as the dot product, and this is the nomenclature we use. Two vectors with the same dot we would use to show multiplication. There's another way of combining them called the cross product, which we're not going to cover very deeply in this class. We're going to take a quick look at it on Wednesday, just because it's kind of interesting what you can do with it, but you're not just going to be responsible for it. An important distinction between these two is that the result of the dot product multiplication is not a vector, it's a number. Whereas the cross product, you'll find you combine two vectors and you get another vector. All right. Before we go any further, I want to make a technical remark here. We are covering now section 9.2 in our book. It is not the 9.2 we covered before, it's the 9.2 at the end of the book. And the page number is 589, but you may find if you look at 589, it doesn't have anything to do with this. You have to page to the back of the book. It's a section that the department added to a very basic book. Okay, so we're going to start looking at the dot product by looking at something called a projection. So let me explain what I mean here. We have two vectors here. We have a v vector and a u vector. And from the v vector, we drop an altitude down to the u vector. And we get our magnitude of the projected vector, which I'm calling here vp, as the length of the vector to that altitude. But this vector is in the same direction as u. Okay? This is called a projection. So using our basic knowledge of trigonometry, we can see right away that, keep this on the screen, the magnitude of this projected vector is going to be the magnitude of the original vector v, and then we're going to use our trig here, right? Does anyone see what the value is right away? Should come to mind pretty quickly. The trig function, what I use to figure out all this x, and I have theta and a right angle and a cosine, that's right. This is the cosine of the angle theta here, the angle between these two vectors. Okay, so also note that VP, as I mentioned, is in the direction of u. Now, I've expressed the magnitude here, but I want a way to express the vector itself. So I need to find a way to express it in the direction of u. But u, of course, we don't know what its magnitude is. But we do know how to make u into a unit vector, right? Recall that if I have a vector u, and I divide it by its own norm or magnitude, that the magnitude of this vector, I'm going to write this carefully here, is 1, right? So this is a unit vector. So if I take this magnitude, Vp, it's just a number, and multiply it by this unit vector, I'm going to get Vp. That is, V projection is V cosine theta times the vector u divided by its own magnitude, or cleaning that up just a little here, Vp is the magnitude of v over the magnitude of u times the cosine of theta. Again, these are all numbers, that times the vector u. So this is a formula you might want to keep in mind. It's of secondary importance to where we're going, but you'll see that it's going to be useful.
Oh, wait.
Okay. At this point, I'm going to give you a definition. I think I want to keep this on the screen for the moment. I'm going to give you a definition of the dot product. The dot product is v dot u, and I'm going to define it as the magnitude, or the norm of u, times the magnitude of the vector v projected onto u. Okay? So recall we defined this projection vector over here. We figured out how to calculate it in terms of v and u. And now we're saying v dot u is just the norm of u times the norm of this projected vector. Well, plugging in, right, if we take the norm of this guy, right, we have u times the norm of v over the norm of u times the cosine of theta times the norm of u again. Well, we have a u that will cancel here, So we have a definition of the norm of u, we have a definition of the dot product, v dot u, is just the norm of v times the norm of u times the cosine of the angle between them. So that's the real important definition here you want to keep in mind. Now, using this definition, we can go back to our definition of the projection, and we can rewrite that in terms of u dot v, and with a little manipulation of what we've just learned, this becomes v dot u over the norm of u squared times u. All right. Recall that v projection is in the direction of u, and this is the constant we would multiply by u to get that vector again. We'll come back to this formula later on. I want everybody to take a deep breath back. This is probably the most kind of abstract and complex thing we've run into so far, and we're not quite done with it. We have to do a little more before it starts to make some physical sense. But keep in mind, this is an outcrop of our original object, the vector. Right? We could look at this from a geometric point of view, but it's going to turn out that thinking of it in terms of vectors has some significant advantages. Okay, let's just very quickly, let's look at some properties of this dot product. As I mentioned, it's a number, it's not a vector. It's a real number for most circumstances we'll deal with. Notice that if you go back to this definition here, you'll see there's nothing about the order of these two vectors. So that gives you a hint already that the dot product has a very common property of numbers. It's commutative. Okay, that's a nice place to start. If we had two vectors that are parallel, and we find the dot product of them, well, what's the angle between two vectors that are parallel?
0 or 100.
Any good answers? 0 or 180 or some 180 if they're kind of in the opposite direction, right? But still. So what is the cosine of 0 or 180? 1. No. Yeah, it's 1. So in fact, if two vectors are parallel like this, their dot product is just the product of their norms. I'm writing this in the wrong order, but that's okay. Okay, that's an important property. Conversely, if the product of the norms is the dot product, and we know that these are parallel vectors. Similarly, if you have two vectors that are perpendicular, their angle is 90 degrees, cosine of 90 degrees is 0. So if two vectors are perpendicular, their dot product is going to be 0. And conversely, if the dot product is 0, we know the two are perpendicular. This is actually a very, very powerful notion that is going to come in handy Okay. Any questions so far? Yes.
You said that two vectors are parallel, they're dot products, and actually can't list this sentence.
Okay, if the two vectors are parallel, then their dot product is exactly the product of their two norms, their magnitudes or their sizes, right? If they're perpendicular, it's 0, so clearly anywhere in between, it's less than the product here, as determined by the cosine of the angle. So, okay. All right. Now we have to do, yes, other questions? Okay. Again, I want you to take a deep breath, because the next part is a little hard. It's not vital you understand every step of this. You should be able to follow this logic. The conclusion is the most important part, because it's going to suddenly make dealing with the dot product fairly easy. All right. So we're going to start with this diagram here of a triangle determined by two vectors u and v. And I'm going to remind you of a result we found on Monday, which is the difference of two vectors can be shown geometrically here. Kind of draw in the rest of the parallelogram here, right? And so recall that the sum of these two vectors is this diagonal, right? But the difference of the two is a vector along the other diagonal, making a triangle. So we have a triangle here. The angle between two vectors is theta. We have two vectors u and v, and their difference is this third side. So what we're going to do here is we're going to start with the idea this is a triangle, and we're going to apply the law of cosines to it. And this is going to get messy for a minute or two, and then we're going to have a really nice result. Okay, so let me remind you that the law of cosines is one of the sides, c, equals a squared plus b squared, the other two sides squared, part of the law of cosines that looks like Pythagorean identity, minus 2ab, and this would be cosine of c, but I'm just going to write it as cosine of theta from my diagram. Okay, c is that opposite, right? So here's my vertex c, and here's my side little c, which is the difference in these two vectors. So c squared, well, c is just the norm or the magnitude of u minus v. So I'm going to write this v minus u norm, but squared equals a squared, which is the norm of v squared, plus u squared minus the 2 times the norm of u times the norm of v cosine theta. All right, that's pretty ugly. We want to simplify this. We want to simplify this in terms of the components, because that's where we're headed. We want to see what the dot product looks like in terms of components. So we're going to convert v into its component form, which we're going to call vx and vy. And likewise, u we're going to convert into its component form ux, uy. All right, so here's where the fun starts. So the norm of v minus u, well, what's v minus u? that's just going to be Vx minus Ux and Vy minus Uy. So the norm of this is the square root of Vx minus Ux squared plus Vy minus Uy quantity squared. But this whole thing is squared, so our square root and our square root are going to cancel. We're going to set that equal to,
You can't see.
oh, thank you. We're going to set that equal to the sum of our norms v and u squared. So what are they, right? Well, they're going to be the square root of dx squared plus ux squared, I'm sorry, vy squared, plus square root of ux squared plus uy squared squared. And now we just have to put in that tail end 2 square root of vx squared plus vy squared times the square root of ux squared plus uy squared cosine theta. Okay. This is where my dear astronomy professor, who was in his 70s, he'd have like these immense equations on the board and getting a little woozy because he's over 70. And fight! Come on, fight! Fight for this, right? Everybody out there? We're almost there. All right. I gotta leave it up there, don't worry. Just have to do a little careful folding. All right, so we can eliminate the square and the square root, and we're going to expand these, right? So Vx minus Ux squared is Vx squared minus 2 Vx Ux plus Ux squared plus Vy squared minus 2 Vy Uy Vy squared. Right, that's on the left side of the sign. Again, if you're following along, that's great. But this is going to get much, much simpler shortly.
Why we need this complicated explanation?
This is because this is mathematics. We're deriving something beautiful and simple. And sometimes math is like that. It's kind of painful, and you have blackboards full of numbers. But trust me, at the end, the result is going to be worth it.
I believe.
Oh, all right. You're very trusting. Maybe you shouldn't be. All right. So this next guy, we have dx squared plus 2 dx dy plus vy squared plus ux squared plus 2ux uy plus vy squared minus 2, and let's just kind of leave this by itself for the moment. Cosine theta. And let's look at this. Well, we've got the left side of the equal sign here and the right side here, and it seems like there's some simplification here, right? These vx's cancel, the ux's cancel, the vy's cancel, and the uys cancel. Let's see what we're left with here. We're left with minus 2 px x minus 2 vy uy. That's all that's left on the left. On the right side, we have 2 vx vy y minus 2. And let's go back and write these for what they are. Square root of vx squared plus vy squared, that's just the norm of vector v. And ux plus uy squared, that's just the norm of vector u. And we, of course, have the cosine of theta. Okay. He thinks he made a small mistake somewhere here. That's where I have to go back and fight. Squared. What's this? 2x. I know I made a mistake here somewhere. Just bear with me. Why is this so hard to find? Okay, let's take a look. Well, it's because when I wrote out the norms of a squared and b squared, right, here, I gave them extra components. These are not here, right? Square root of vx squared plus vy squared is just vx squared plus vy squared. This component doesn't belong here at all. Okay. Nobody caught me at that. Okay, so that makes things much easier, doesn't it? Did everyone see what the mistake I made? It's kind of the opposite of what most algebra students do. Most algebra students do this. They go a plus b squared equals a squared plus b squared. That's right. That's kind of the, all freshmen would like that to be the case. I went from this to this. All right, moving right along. Because now we're right where we want to be. All right. We can divide through by minus 2, right? Get rid of the minus 2s, this becomes a plus. Get rid of that minus 2. Now we have the result we've been looking for. The norm of v times the norm of u times cosine theta, which has another name. What's the other name we started with? What's the subject of today's lecture?
Dot product?
Dot product. That's the dot product, right? That's just equal to vx ux plus vy uy. Oh, let's get our heads wrapped around this. We've got two vectors. We have their components, vx uy, ux uy. And now we have a way to compute the dot product just looking at those components. Well, I mean, I think that's fabulous. That's so fabulous, I'm going to get a nice big, nice clear, I want you to cogitate that for a second. You can find the dot product. There kind of seems like a pattern here, doesn't it? In fact, although it's beyond the scope of this course, we're going to find that in 3 dimensions, that pattern continues. And if you get into higher mathematics, where we look at higher dimensions, the pattern will continue. All right.
Maybe can you just go back to the page that you had before? We had all the final product.
All the numbers.
Yeah.
This guy?
Yes.
Here we have the dot product, the norm of v, the norm of u, cosine theta, and here we see it's just the sum of the product of the x and y components.
I have a question.
Yes.
How did you get rid of the 2's on the right side of the equation?
Well, I divided through by -2. So I had a -2 here and a -2 here. So that
No, you have a positive 2 there.
I had a -2. I put a plus through it.
Oh, okay.
When I got rid of the minus, I made it a plus. Maybe I should have taken an extra step there. And I get rid of the other -2 because I just divide through. Okay, this is just a beautiful result.
Amazing.
But, let me put it back up there. Right? Because we know v dot u is the norm of v, the norm of u, times the cosine of the angle between them. So, here, let me put that too. It's kind of in front of you. Right? Using this, what if we happen to know the magnitude of the vectors and their components? Now we can instantly calculate the angle between them. Right? Dividing by these 2 components and finding the inverse cosine, we get this equation, which says that the angle between them is the inverse cosine of the dot product divided by the 2 norms. Well, this wouldn't be very useful, except we know how to find the dot product from the components. We know how to find the norms from the components. It's a little complicated, but in practice it's not going to be too hard. All right, so what we really need now is we need to come back to Earth, and we need to do an example. So here's our example. This is, I think, actually from the book. The question is, what is the angle between these 2 vectors? So the first thing we want to find here, u dot v. I want to find the dot product. Well, that's easy. The x components, 3 times 2, plus the y components, 5 times 8, -8. Right? And that gives us -34. So that's the first part of that equation. We're also going to need the norm of u. Okay, that's just that Pythagorean construction. Square root of 3 squared, which is 9, plus 5 squared is 25. That's going to be square root of 34. Did I get that right? I heard a noise. Usually means I got something wrong. Same thing here with the magnitude of v. Square root of 2 squared, 4, plus -8 squared, 64. Square root of 68. And combining all this, we're looking for the cosine inverse of the dot product, -34, over the square root of 34 times 68. Now this, if ever there was one, is a calculator problem. Right? If I ask you for an exact answer, which I wouldn't for a problem like this, that's pretty much all you can do with it. You might want to multiply these and try and reduce it, but I don't think you will. So let's make sure we're in degree mode, because I want to know the degrees today. So cosine inverse minus 34 divided by square root 34 times 68. 135 degrees. Pretty amazing. Now, we could do this without vectors and without the dot product. We could figure out these triangles and figure out their angles and figure out the difference in the angle, but this is nice and straightforward. It's the prettiest result you're going to see about vectors in this class. There are other pretty things we can show you for vectors, but take a little more time. Okay. Any questions about that?
Could you put that up?
Yeah.
Could you put that back up for a second?
Okay. Sorry.
Thank you.
Okay. The next problem is I'm gonna kind of look at it the same way. It's kind of a trick problem. It wants you to figure out something here about the dot product. Same question, what's the angle between these vectors? Let me skip finding the norms for the moment. Let's just go right to the dot product, right? So 2 times minus 1 plus 1 times 2 is 0. Does anyone remember what we said about the dot product being 0? They're perpendicular, yeah. There's a 90-degree angle between them. So that's a really nice feature. We don't have to go through all the rest of the trouble. We can just say right away, perpendicular. Similarly, if, well, not similar. If they were parallel, you'd get some kind of number and we'd have to divide to see if it was 1. Okay. All right. One more question, one more problem here. This is not the same problem. This is a little different. It says, find the components of U along V. So let's first kind of understand what that means. Have a vector U, have a vector V, and I drop an altitude from U to V, and I'm going to have this vector here, which I previously called U projection or U projection onto V. So, recalling from earlier, I mentioned that I guess I'm not going to go back to where I was. We have a slightly different formula for this vector. The projection of U onto V is the dot product divided by the norm of U squared times the vector V. Sorry, that doesn't sound right. Yeah, that's right. I don't want to steer you wrong. Let me go back and verify that. Yes, I'm confusing myself because, because I'm switching U and V here. This actually should be V, the norm of V, I was right. Okay, so let's apply this formula to that problem, right? right? So first we want to find the dot product of these two. Again, that's pretty simple. 1 times minus 2 plus 4 times 1 is just 2. That's u dot v. So we have u dot v 2 over the norm of v squared. Well, what's the norm of v squared? The norm of v is square root of two squared plus 1 squared, which is square root of 5. But if I square that, I just get 5. So this is 2 over 5. And then the last part of this is v, right? So I have, right? I have 2/5 times my vector v, negative 2, 1. So this becomes minus 4/5, 2/5. That's the position vector components for the solution. Okay. That operation's seems a little obscure, finding the projection. We're going to see an application of this after the break. But before you go, would you please pick up the worksheet? Okay. Has anyone who's been here since quarter after not gotten down to at least 9? Could you repeat that? What? Assuming you came back at quarter after, you are a person of the category who's in the room at quarter after. Have you not, has any of those people not gotten to at least 9? You just came in.
Yeah, I know, but I don't understand what's going on. I can't even do the first one.
Okay, all right. 1 through 6 are kind of warm-ups. Recall that take a vector u and make it a unit vector. In other words, change its length to 1. We just divide it by its norm. Okay? Now, you don't have to, number 1, 2, and 3, the question is, are they unit vectors? So what you want to do is see if this vector, the norm of this vector is 1. So if the components are dx and dy, the norm is the square root of dx squared plus dy squared. So that's all 1, 2, and 3 are. You plug in and you see if it's 1. So for example, 2/3 squared plus 1/3 squared, what's that? That's 4/3, and 1/3 is 5/3, square root of 5/3. Not a unit vector. Did that help? If you want something kind of visual, here's a vector. Its components are 2/3, 1/3. I want to know if this is 1 or the length is 1 or not. So that's how I can find out. How about number 4? before, just using my little formula here. So, for example, 4, 5, and 6. So I'd say, well, I've got a vector. I want to divide it by its norm. So the vector is 3, 3. And its norm is the square root of 3 squared plus 3 squared. That's 3, 3 divided by what? 3 square root 2. So this vector becomes 3 over 3 square root of 2, 1 over the square root of 2, 1 over the square root of 2. That's the unit vector in the same direction. We know it's a unit vector because if we find the square root of this plus the square root of this squared plus the square root of this squared, what's that? This squared is a half, this is a half, half plus half is 1, square root of 1 is 1. So it's a unit vector. Okay. I guess I should go over 6 just because I think the notation there might be the problem for some people. Want a unit vector that's equivalent to I plus j. Does anyone remember the definitions of I and j?
I is a 1 and 0.
1, 0. It is a unit vector already, right? This isn't. This is, right? And j is
0, 1.
0, 1. So I plus j is just 1, 1. Okay. I want to make that into a unit vector. I divide by its norm, which is the square root of 1 squared plus 1 squared, which is square root of 2. So this just becomes 1 over, oh, it's the same answer as that first one. All right. Well, this is in the same direction as 3, 3, right? I, j. Well, 3, 3. It's the same direction. So when I find the unit vector has to be in the same direction but 1. It has to be the same. 5 is different.
Question.
Yes.
I'm a little, it's not really, I'm not really comfortable with it, so does that mean that the number 6 and number 4 are also in the same direction?
Yes.
So
3, 3, and I plus j are in the same direction.
So could
See,
we,
I is 1, 0, j is 0, 1. So I plus j is 1, 1.
yeah, so
And 1, 1 is in the same direction as 3, 3.
couldn't we just go ahead and say because they're, let's say vx and vy are the same thing, that's because it's 3 and 3, could we say just like 4, 4 is in the
If
same
you're
direction?
really smart, you could say that. I mean, you know, you're correct. Absolutely correct. But, I mean, that's fine. Okay, so now we want to do hard problems, right? Has anyone not done 7? Has anyone not tried 7? Is anyone confused about how you would figure out 7? This is an accident waiting to happen. So I want a projection of V onto U. So I've written this down, that it's the dot product of V and U divided by what? Norm of U squared times U. Does that look right? So how does that translate? V is 9, 2. U is 1, 0. So the dot product, once again, is really easy. 9 times 1 plus 2 times 0. That's just 9. The norm of U, wow, that's easy too. Square root of 1 squared plus 0 squared is just 1. Squared again is 1. So it's just 9 times U, which is 9 comma 2. So that's just going to be 81 comma 18. That doesn't seem right at all.
Yeah.
That can't even be. I just look at that, it doesn't pass the smell test, does it? What did I do wrong there?
Why are you multiplying 9 by 9 twos? Shouldn't it be 1 0?
9 times 1 plus 2 times 0.
Why did we multiply vector by vector in vector?
Yeah.
We should get a vector.
It's a vector, but it's wrong.
No, vector u multiplied by vector.
No, my question is, you should be multiplying by u at the very end, but you're multiplying by v again.
Oh, thank you. I knew something was
Okay,
wrong.
that's what
Thank you. 9 times 1 comma 0.
Times 9.
Okay, so that's 9, 0. There's more to this problem than meets the eye. I'm going to come back to this problem in a minute. Let's try another one. Like V is 5, 3, and U is minus 2, 7. So the dot product, 5 times negative 2 is minus 10. 3 times 7 is 21. So that's, everybody do that in their head? 11. Now we need the norm of U. So the square root of 4 plus 49 squared. So it's just 53. And that times U, which is negative 2, 7. So that's negative 22 over 53, comma,
No, negative.
it's a negative 2.
Oh, yeah.
77 over 53. Questions? All right. Okay, now we're back to find the angle between two vectors. Right, we had a formula for that. Definitely a good formula to either figure out how to figure it out, right? I mean, how would you do that? V dot U equals the norm of V, norm of U, cosine theta, which is also equal to Vx Ux plus Vy Uy. From there, you solve for theta, right? Cosine theta equals Vx Ux plus Vy Uy, the dot product, right? Over and then you find the inverse cosine, and that's it. So that's one way. The other way is you